second. Okay, we're going to take our Taylor and Maclaurin polynomials and we are going to write them as series.
That's wild.
I don't know if I can handle that.
I've been waiting on those.
Have you?
So much you smoke.
Okay, so a Maclaurin polynomial. We evaluate the function at 0. We evaluate the derivative at 0 times x. We evaluate the second derivative at 0 over 2 factorial times x squared, right? And we keep going forever. So do you agree that we could write it like this? F to the k of 0 over k factorial times x to the k.
Okay, so let's do the Maclaurin polynomial at the sum.
Well, right now this is like,
Remember, what you were right.
hold on. Hold on. Because, yeah, because we're gonna do these infinitely. Okay, so here would be like the like we could say like the 5th degree polynomial and put a 5 there, or the 10th degree polynomial and put a 10 there, right? Okay. If we wanted a Taylor polynomial with a center at x naught, then it looks like this, right? Instead of 0, we have x naught, and instead of x to the k, we have x minus x naught to the k. Okay, that's taking what we did with our Taylor polynomials and writing them as a series. Now, what we're going to do is we're going to do that, but infinitely. Okay, I know that this is something that I think a couple of you have mentioned over the course of the past week.
So is that k equals 0 below the sum, or k equals 9?
K equals 0. So we start by plugging in 0, and then 1, and then 2, and then...
All the other zeros are no's.
And this is x naught, the subscript is.
Yeah.
Well, and maybe you would like it better if it was like C.
Yeah, I like that better.
Like C for center.
C is so much nicer.
Right. You like that better? Okay. Now, we are going to do this infinitely. It's really okay if you don't. I'll let you take a picture.
Yeah, I'm just going to write that for some.
So now we're going to do this infinitely. And if we want to make these C's, you can go ahead and do that. It bothers me. Okay, so once we make it infinite, we call it a Taylor series or a Maclaurin series. This is what is important.
So k is what n normally is, and n is something else.
K is that.
Why do they do these things?
Because the
Okay, so here, Bailey, here we stopped at n. Here we're going infinitely. Now we still have, you know, the function evaluated at 0, the derivative at 0 times x, the derivative at 0 over 2 factorial times x squared, but then we're just going to write it infinitely. Okay, so here we have from 0 to infinity. Now we're still probably going to use n's instead of k's, but when we generalize things, we like to use different variables for some reason, okay? But we're still going to use n's. All right, so not to fear. Well, hello. That is, it is B21, but Miss Cronky is not in B21 right now. I'm trying to think of where she would be. Second hour.
That's embarrassing.
Try down in Miss Kelly's room, like B18. Okay. All right. So, for example, I want a Taylor series for e to the negative 2x at c equals 0. So basically this is a Maclaurin series. Sometimes I'll call it a Maclaurin series. Sometimes I'll call it a Taylor series centered at 0. You should go with the flow, right? Okay. If our function is e to the negative 2x, what is our function evaluated at 0? Okay. Our derivative would then be negative 2 e to the negative 2x, which means our derivative at 0 would be negative 2. Let's get a couple under our belt here. The second derivative would then be 4 e to the negative 2x, right? Okay. And without actually taking the derivative, what is going to be our third derivative? Negative 8. We see a pattern, don't we? And we can catch on to that pattern without having to write everything down, right? So, our sum is 1 minus 2x plus 4 over 2 factorial x squared minus 8 over 3 factorial x cubed. For kicks, what would the next derivative be?
Plus 16 over 4 factorial.
And that would keep going. So what we get to do now is we get to actually write this as a series. We get to say, okay, this is the sum from n equals 0 to infinity. All right, I'm already going to catch the pattern. N factorial is in the denominator. X to the n is what we're multiplying by. What's in our numerator? Okay, so really we could even say negative 2x is being raised to the n power as we go through, right?
Can you work like that, or like yesterday when we had this, get it all up and have it look like an alternating, or can you leave it like that?
Let me think here. Like you could see it as like negative 1 to the n, 2x to the n over n factorial. Is that what you're saying?
Yeah.
I would be okay either way.
Does that just depend on what you need to do in this series after you write it?
Potentially, yeah. I'm trying to think of. Let me look at the multiple choice here.
You guys repeat we do negative 2x to the n over n factorial, or negative 2x to the n over n, because I guess usually we sleep on it.
Okay. Yeah, let's go ahead and just stay in the habit of making this the negative 1 to the n separate from everything else. Okay, because that's probably what you're going to see as far as like answers for multiple choice tests. And depending on like the author, you might see it both ways, but let's just be in the habit of separating out the negative 1 to the power. Okay, so here is our series for e to the negative 2x. Okay, so this infinite polynomial is approximating e to the negative 2x at 0. Now I lost my notes. Here we go. All right, you ready for some fun?
Was this not fun already? I actually like this question.
Okay. So we're going to be able to figure out this little pattern here pretty quickly. F of pi over 4. Whatever you want. I'm going to keep it as this because I'm in trig mode for pre-calc here. Our derivative. So another radical 2 over 2, right? What's going to happen with our derivatives? Yeah. Positive, positive, negative, negative, right? So we know that our next two derivatives are going to be negative sine of x at pi over 4 and negative cosine of x at pi over 4. And that pattern is just going to keep going, right? We've seen that. Anytime we have a cosine or sine, we're going to have a cycle of 4, right? All right. So our Taylor series would be radical 2 over 2 plus radical 2 over 2x minus pi over 4. And then we have minus radical 2 over 2 divided by 2 factorial x minus pi over 4 squared minus radical 2 over 2 over 3 factorial x minus pi over 4 cubed. And that pattern's going to keep going with the positive, positive, negative, negative, positive, positive, negative, negative. Now, this is what I like about this. My husband and I came up with 2 different ways to express this series. I'll give you a couple minutes to talk about it with your class. How in the heck are we going to get that positive, positive, negative, negative, positive, positive, negative, negative pattern in our series? Obviously, negative 1 to the n power isn't going to work.
Well, it'll still cancel out the other cap. That makes sense. So we have to find something. If you have one bottom.
All right, any ideas? Okay.
First off, we can still use the sine.
Okay.
Right, and then inside it we could have something
So your idea is to use sine, right?
Yeah, I was thinking pi over 4x plus pi over 4 maybe?
Well, basically we need all of the odd numbers with pi over n, pi over 4, right?
That would I be able to do like a 2x plus?
So that would give you the positive, negative radical 2 over 2 over n factorial times x minus pi over 4 to the n. That would be what you were trying to describe, Josh. Okay.
Ooh, wait a second. You put x times x power 4 to the n on this one. Or did you not do it? I don't think you did it the last one. Maybe you did.
2x to the n. On this one.
I thought that was the root. Oh. I was assuming that there would be an x at the end at the end.
There is an x to the n.
Oh.
Why is the n?
I don't know. It doesn't need to be.
It looks pretty that way.
Ooh, I was referring to something.
All right, so that's one way. There is a way to do it without involving sign. There's a way to do it with -1 to a power. Ready for this? First, I'm going to factor out -2 over 2. I mean positive radical 2 over 2. Okay, so we have radical 2 over 2 times 1 plus, I can only get it to where we get positive, negative, negative, positive, positive, negative, negative.
And start at 1.
Right. So I'm still starting at 0, but the pattern that I have only has 1 positive and then 2 negatives. So I'm going to go ahead and keep this 1 out because I can't get it to be positive, positive, negative, negative. Okay? So if we take -1 to the n times n plus 1 over 2. Okay. So check it over. When you plug in 0, we get -1 to the 0, which is 1. When we plug in 1, we get -1 to the first power, which is negative. When we plug in 2, we get -1 cubed, which is negative. And it's going to keep going. And so then, but since we had to start at 0, and we're starting with our second term instead of our first, we're going to have to do a little bit of an adjustment and say x minus pi over 4 to be n plus 1 over n plus 1 factorial, since we kind of had to do some rewriting. You like the other one better?
Yes.
Now, I'm showing you this example because it's crazy. All right? And sometimes we like to see some crazy things, and then what we do next is going to seem simple, right? Okay. Now, no. Never a test question, ever.
Thank you.
You're welcome. Okay, now, here's what's nice about Taylor-Maclaurin series. There are 3 series that once we've done them once, we can remember them, and you will remember them, and then it can make other problems go faster, okay? Here are the 3 that we are going to remember. Okay? E to the x. E to the x at 0 is 1. What's the derivative at 0? What's the second derivative at 0? What's the third derivative at 0? So, in general, we can write x to the n over n factorial for our series. Okay. Now, I am going to tell you that sometimes you will be asked to write a series. Sometimes they will ask you for, like in this case, the first 4 terms and the general term. That's what I've written right here. First 4 terms and the general term. This is writing the series without the summation. Okay, so you're kind of like stretching it out. Right? Okay, now let's think back to what happens with cosine. When we, cosine at 0 is 1, right? Then we take the derivative to be negative sine, and negative sine of 0 is
0.
okay. And then we take that derivative to be negative cosine, and so we're left with negative 1, but that's with the x squared. Okay, remember every time we take the derivative, we're going to get cosine, negative cosine, sine, cosine, negative sine, negative cosine, sine, cosine, right? And the cosine of 0 is 1, but the sine of 0 is 0. So what happens with cosine is we're only getting the evens, and we're going to alternate our sign because of that positive, positive, negative, negative effect. So how would we describe this in general? Okay, we would have x to the 2n. It's also alternating, right? And then in our denominator is 2n factorial. Remember it. I mean, those aren't bad to remember, right? Okay. And really, if you didn't remember it, coming up with them, you wouldn't have to use a lot of work to get them. Okay? So then sine. The sine of 0 is 0, but then we take its derivative cosine and evaluate that to be 1. So we're starting with x to the first power. And then the second derivative is negative sine of x. Well, that is 0. The third derivative is negative cosine. And so we get negative x cubed over 3 factorial. The fourth derivative would then be positive sine. Fifth derivative would be positive cosine, evaluated at 0 is 1. So what's happening here is we get all of the odds, and they alternate. So we still have an alternating series, but now we have x to what power? N.
Well, would it be 2n minus 1?
It'd be 2n plus 1 because we always begin at 0.
Okay.
And so 2n plus 1 would be the factorial that would have to match the power. Okay. So, if we can work with these basic series, it can help save us some time later on. Okay? And here are some things that we can do with problems that get more complicated. Okay? With these series right here, we can substitute things in for x into a series we already know. For example, like the series of e to the 2x, we can take the series of x and just replace all the x's with 2x, and we cut our time in half because we already know the series of e to the x. Okay. We are going to be allowed to multiply or divide a series by a constant and or a variable, and I'll show you what that looks like here in one of our examples. We're going to do the example x cosine of x. Well, we already know the series for cosine of x, and so we can just simply multiply the x to it. Or if we have cosine of x divided by 2, all we have to do is take our series and divide it by 2. Okay. We are allowed to add or subtract two series together. And then some tips that we already know. We know that we are allowed to differentiate or integrate a series. And we know that we can look for geometric power series to help us. Okay, so those are two things that we talked about a lot in this weekend's video. Okay, so what we're going to do today and tomorrow is focus on those first three. Tomorrow we'll do a little bit with the differentiate and integrate as far as Taylor series are concerned. All right, but this is kind of squishing everything together. Okay, and it is nice because we don't have to sit there and find every single derivative. We can remember some patterns and use those to save us some time. We like to save time, right? Okay. I have 1, 2, 3 examples. You ready? We do have 10 minutes to get through these 3. So you want to take a picture of this and fill it in? You are done? Okay. So, here's our first example. Sine of x squared. So we know that sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, blah, blah, blah. Our general term, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. We know that we're going to remember it. So what we can do for the sine of x squared is anywhere there's an x, we are going to replace it with an x squared. So this is x squared to the first. And this is x squared to the third. And this is x squared to the fifth. And this is x squared to the seventh. And in our general term, okay, we don't even really have to think too hard. We're just going to say x squared is being raised to the 2n plus 1 power. All right, and now all we have to do is simplify using simple algebra rules, okay, way back from middle school even. Okay. So we have the sine of x squared becomes x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. And instead of trying to figure out what the heck that pattern is, we can just say x squared to the 2n plus 1 is x to the 4n plus 2. I'll tell you what. It is either going to ask you to write it as a series or write the first 4 terms and the general term, which is what this is.
Okay.
So for right now, I'm just going to leave it like this. If we wanted to write it as a summation, then we could write it like this. Right? You would just do the sum of that general term if you needed the series. Okay? More often than not, though, we're going to leave it like this. Okay? Isn't that nice?
So you pretty much just put the general term into the easy, like you got what you need.
Yes.
Okay.
Yep, just make sure you begin at 0. Okay?
Yeah.
All right, next one. X times cosine of x. Okay? Literally, all we're going to do is take x and multiply it to the cosine series. So the cosine series is all the evens, right? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Okay? We literally have x times our cosine series. And just using algebra rules, we're going to distribute that x to every single term. So if we distribute into those first 4 terms, we get x minus x cubed over 2 factorial plus x to the 5th over 5 factorial minus x to the 7th over 6 factorial. And you can either look at that pattern and figure it out, or you can use simple algebra to say x times x to the 2n is simply adding those powers together to be x to the 2n plus 1. Bailey is just smiling like, what do you mean?
There's no more.
Yeah.
No.
It looks pretty scary.
So did I say we were allowed to add 2 series together?
Yes.
Did I say we were allowed to divide or multiply by a number?
Yeah.
Okay, so we're just doing 2 of those together. Maybe it would help you if we just said this was 1/2 times e to the x plus e to the negative x. We don't have to worry about that division quite yet. Okay, let's first focus on e to the x plus e to the negative x. E to the x. I'm going to write that in red. What is e to the x? 1 plus x squared over 2 factorial x cubed over 3 factorial plus x to the n over n factorial, right? Okay. In green, I'll write e to the negative x. What's going to happen with e to the negative x? All of our odd powers are going to turn negative. Do you agree? Okay. So we're going to get 1 plus negative x plus negative x squared will stay positive plus negative x cubed will turn negative And when we put a negative x into our series, we're going to write it as an alternating series, right? Well, and really for now, heck, it's not our final result, so it's fine to leave it like that for right now. Okay? So, when we add these two series together, what happens? What is 1 plus 1? Thank you. What is x? Okay, so there's that, right? What is x plus negative x? 0. And then we have x squared over 2 factorial plus x squared over 2 factorial. You get 2 of them, right? Then what happens to x cubed over 3 factorial minus x cubed over 3 factorial? That's going to go away, right? So what's going to happen here? We're going to get doubles of all of the even powers, right? How would we write that in general? Okay, so make every n a 2n. And then notice how these are all doubled, right? And so we would need the double. Well, for now, and so then yes, we do have that 1/2 out front, which means it's going to cancel out all of the doubles that we just did, right? And so we're going to be left with 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial. And in general, we're going to have x to the 2n over 2n factorial. Okay. So pay attention to the instructions. If it says, write the first however many terms in the general term, this would be the 4th. If it says to write the series, then you would need to go ahead and do one step further and equal 0 to infinity of x to the 2n over 2n factorial. All right, so reference your gold sheet for your homework tonight. And then we will do some more practice tomorrow. Okay? Good class today, guys.